Okay, welcome dear students. This is the third video about group theory. In the last two videos, we had discussed about the great orthogonality theorem and character table, the format of the character table, etc. And in this video, we are going to discuss about the construction of character table. An example using great orthogonality theorem, how can we construct character table? Okay, we are using five important rules that are actually the consequence of great orthogonality theorem, and making use of these five rules we are going to construct character tables. And first we are discussing C2v character table for C2v point group. Okay, we know that in a C2v point group there are four elements: E, C2z, sigma v xz, and sigma v dash yz. And it is an abelian point group. We know that C2v is an abelian point group. That means all the elements are commute to each other. Therefore, each element is a class by itself. That means here E1 is a separate class, C2 is another class, sigma v xz a class, like that. Each element is in a class by itself. So how many classes are there? There are four classes. In C2v point group, there are four classes. And we have studied from the great orthogonality theorem from rule 5 that number of irreducible representations is equal to number of classes. Okay, here number of classes is equal to 4. Therefore, there are 4 irreducible representations in C2v point group. Okay, C2v point group contains 4 IR, 4 irreducible representation. Let the dimensions of the IR be L1, L2, L3 and L4 are the dimensions of the IR. Say we are using the Beathes notation, gamma 1, an arbitrary notation, gamma 2, gamma 3 and gamma 4. Okay, dimension of IR gamma 1 is L1, dimension of the IR gamma 2 is L2, and like that. And we know that according to rule 1 of great orthogonality theorem, sigma Li square is equal to h. That means sum of the dimensions of the IR is equal to order of the group, and that is equal to 4. Okay, sum of the dimensions of the IR will be equal to order of the group. That is from the rule 1 of the orthogonality theorem. And therefore, we have 4 IR. Dimensions are L1, L2, L3 and L4. Therefore, L1 square plus L2 square plus L3 square plus L4 square is equal to 4. Okay, since the dimensions, the LIs can't be 0 or negative. The dimensions cannot be 0. A zero matrix is not possible for a particular element. A negative, that is also not possible for the dimension. Dimension cannot be 0 or negative. Okay. Therefore, L1 is equal to satisfy this condition, L1 square plus L2 square plus L3 square, L4 square should be equal to 4. Therefore, to satisfy this condition, L1 should be L2, L3 and L4 also are equal and is equal to 1. That means all the irreducible representations are one dimensional. Okay, L1, L2, L3 and L4 are equal. That is only condition satisfy this equation, L1 square plus L2 square plus L3 square plus L4 square. Since L1's Li's can't be 0, dimensions can be 0 or negative, therefore only one possibility, that is all these dimensions should be equal and its value is equal to 1. That means all the IRs of C2v point group are one dimensional. Okay, yes. Then in any group, that is one of the thing you have to keep in mind. In any point group, there would be one dimensional representation IR, say gamma 1, which would be totally symmetric. In every point group, the one irreducible representation is there would be a one-dimensional representation which is so totally symmetric. That is totally symmetric means all the characters is equal to 1. Okay, in all point groups, like, there would be one irreducible representation that is totally symmetric, and that is a one-dimensional representation, and that is totally symmetric. That means all the characters are equal to 1. So in every point group, the first irreducible representation should be like this. That is, all the characters are 1. That is a one-dimensional representation. We are denoting it as gamma 1, an arbitrary notation. And this column also we can fill because we know that all the IRs are one-dimensional. In the later slide, we have studied that in C2v point group, all the irreducible operators. There are 4 irreducible representation because 4 classes. Number of IRs is equal to number of classes. There are 4 classes, and all these IRs are one-dimensional. Therefore, character of E is equal to 1. We know that we have already studied that the character of the identity operation is equal to dimension of the irreducible representation or the representation. Okay, these all are one-dimensional. Therefore, character of E in all these representations should be 1. Therefore, these all characters are 1. So we get the row and this column. Okay, very easy. Now we want to get the other characters. We are arbitrary using the notation A, B, C, D, E, F, G, G, K, M. I'm not using I, J, H, etc. because they are used as irreducible representation and order of the groups where I'm using G, K, M, etc. Okay, and further from our rule, that is I think it is rule 1 or rule 2, that is sum of the characters of, sorry, this is chi I r square. Characters, the square of the characters of a representation is equal to order of the group, that is equal to 4. Okay, we have already studied that from the rule of orthogonality theorem, that is sum of the squares of characters of a particular representation is equal to order of the group. That is sigma r chi I r square is equal to h, and h is equal to here 4 here in the case of C2v. Therefore, it should be 4. And this representation, this is the first representation, already satisfies this rule because 1 square plus 1 square plus 1 square plus 1 square, that is equal to 4. That is already satisfied. Therefore, for other representation, we can write 1 square plus a square plus b square plus c square is equal to 4. And 1 square plus d square plus e square plus f square is equal to 4. 1 square plus g square plus k square plus m square is equal to 4. Because sum of the squares of the characters in every representation, in a particular representation, is equal to order of the group. That is taking the square of each character and summing all the elements. Okay, we get the order. Okay, here order is equal to 4. So 1 square plus a square plus b square plus c square is equal to 4. I think this is actually is a rule. This is a rule 2. Rule 2 of the this is the rule 2 of orthogonality theorem. That is sum of the characters of sum of the squares of the characters of a particular representation is equal to order of the group. That is here 4 here. And this is possible only if, these equations are possible only if A, B, C have values either 1 or minus 1. Okay, because all are one-dimensional representation, because therefore value should be 1 or minus 1. Because one-dimensional representation means if representation is one-dimensional, then the character and matrix are identical. Because the character is the sum of the diagonal elements. In the case of one-dimensional representation, only one element is there, and that is the character itself. Okay, therefore it should be 1 or minus 1. And these equations are also satisfied only all these values of a, b, c, d, e, etc. is either 1 or minus 1. satisfy this condition, to satisfy this equation, these values should be a, b, c, d, e, f, g, etc. should be either 1 or minus 1. And according to the orthogonality rule, that is rule 3, I think it is a rule 3, that is the characters are orthogonal. That is sigma r, chi I r, chi j r is equal to 0 when I not equal to 0. By squaring the characters of a particular representation, we get order of the group. By multiplying the characters of different representation and sum over all the operation, we get value is equal to 0. That is, they are orthogonal. These are normalized. In a particular representation, characters are normalized. In the case of two representation, they are orthogonal. That means their product will be equal to 0. Sigma r, chi I r, chi j r is equal to 0. So among chi 1, chi 2, chi 3 and chi 4, each has to be orthogonal with the gamma 1. Chi 2, chi 3, chi 4 should be orthogonal with the gamma 1. So we can write, if we consider gamma 1 and gamma 2, therefore 1 into 1 plus 1 into A plus 1 into B plus 1 into C is equal to 0. And if you consider gamma 1 and gamma 3, then again 1 into 1 plus 1 into D plus 1 into E plus 1 into F is equal to 0. And again gamma 1 and gamma 4, 1 into 1, 1 into G, 1 into K, 1 into M is equal to 0. Okay, this is possible. Okay, all the characters should be 1 or minus 1. This is possible if there are 2 plus 1 and 2 minus 1 in each of gamma 2, gamma 3 and gamma 4. That is, in all these values, okay, 2 are plus 1 and 2 are minus 1. Already first character is 1 here. First character is 1. Therefore, other 2 will be minus 1. Okay, this is possible if there are plus 1, 2 plus 1 and 2 minus 1 in each of gamma 1, gamma 2, gamma 2, gamma 3 and gamma 4. Gamma 2, gamma 3 and gamma 4 contains at least 2 plus 1 and 2 minus 1. Already plus 1 is here. So another 1 is plus 1 and another 2 is minus 1. Okay, by considering all these factors, considering all these, that is, all the characters should be 1 or minus 1, and first representation is totally symmetric. That is a case of all, for all representation, that is totally symmetric. And other representation, two characters will be plus 1 and other 2 will be minus 1 to satisfy the orthonormal condition, normality condition and orthogonality condition. By arbitrary fixing all these values, we get the values like this. That is, here 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1. Okay, so we can check. Okay, is it normalized or orthogonal? In the case of here, this representation. Okay, 1 square plus 1 square, 1 square plus 1 square plus minus 1 square plus minus 1 square should be equal to 4. It is 4 itself. Okay, and also this 2 should be orthogonal. That is, multiplying this with this and sum over all the operation, we should get 0. That is 1 into 1. Okay, 1 plus 1 into 1 plus 1. Okay, 1 into minus 1. Okay, minus 1 plus 1 into minus 1 minus 1 equal to 2 minus 2 is equal to 0. By considering all these, 1 gamma 1 and gamma 3 should be orthogonal. You can check it. Okay, gamma 1 and gamma 4, you can also check it. 1 into 1, 1, 1 into minus 1, minus 1, 1 plus minus 1, 0, 1 into minus 1, minus 1, 1 into 1, plus 1, 0. Okay, all these two conditions are satisfied. Orthogonality and normality conditions are satisfied. That is, sum of the squares of characters in a particular representation is equal to 4, and multiplying the characters of one representation with another representation and sum over all the operation, we will get 0. So these all conditions satisfied. This is the characters of IRs in the C2v point group. And we are arbitrarily writing the irreducible representations are gamma 1, gamma 2, gamma 3 and gamma 4. And by Bethes notation, we already studied about Bethes notation. This representation is all one-dimensional representations are represented as A or B. Therefore, this is A or B, And if the representation is symmetric to the principal, this is a principal axis, this is symmetric, that means character is 1, therefore it is A. And it is symmetric to the first vertical plane. There is no another subsidiary axis, therefore we are considering the vertical plane. Therefore vertical plane character is 1, therefore it is symmetric to the first vertical plane, therefore it is A1. That is gamma 1 is A1. And gamma 2, this is also one dimensional and symmetric to the principal axis, therefore it is also A. Okay, but it is anti-symmetric to the vertical plane, therefore it is A2. Okay, and this is one dimensional, but it is anti-symmetric to the principal axis, therefore it is B. But it is symmetric to the vertical plane, therefore it is B1. That is gamma 3 is B1. Okay, and this one anti-symmetric to the principal axis, therefore B. It is also anti-symmetric to the vertical plane, therefore it is B2. Therefore gamma 1 is A1, gamma 2 is A2, gamma 3 is B1, gamma 4 is B2. And look at the area. This is area 1, this is area 2 of the character table. This is area 3 and this is area 4. In area 3, we have already discussed that it contains 6 symbols, x, y, z, that is Cartesian coordinate, and rx, ry, z, that is rotation about the x, y, z axis. We can look at what will be the basis for this representation. Okay, these are actually basis for the representation in one term. Okay, take x. What are the transformation of x? X, we can consider x as a Cartesian coordinate or x as a vector. Then E transforms x by itself, therefore character is 1. C2z, it is C2z. Okay, x become C2z, x become minus x, therefore character is minus 1. Sigma v xz, sigma v xz, x coordinate become itself, no change, therefore 1. Sigma v yz, x become minus x, therefore minus 1. That is 1 minus 1, 1 minus 1. What is this one? Where is that? 1 minus 1, 1 minus 1. That is x. That is x transforms as b1. We are saying like this, x transforms as b1. X coordinate transforms as b1, or b1, the basis for b1 irreducible representation is x. Okay, and consider y coordinate or y vector. Okay, E transforms y itself, no change, 1. C2z, y become minus y, minus 1. Sigma v xz, y become minus y, therefore minus 1. Sigma v yz, y is itself, no change, 1. 1 minus 1, y minus 1, 1. Yes, it is there, 1 minus 1, minus 1, 1. Therefore, it is y. It is basis for this representation. B2 representation is y, or B2 y transforms as B2. That is the term we are using. Y transforms as B2. Okay. Next we consider z coordinate. Z coordinate, E no change, 1. C2z no change. Sigma v xz no change. Sigma v yz no change. All the characters are 1. Therefore this is a totally symmetric representation. So its basis is z, or we can say z transforms as A1. Okay, that is the area 2. And also this xyz also represent px, py, pz orbital. We can also look like that. Px, py, pz orbital. Consider px orbital. This is the x-axis, this is the y-axis. Here plus sign, minus sign. E transforms px orbital by itself, no change, therefore 1. C2, the C2z is like this, perpendicular to this plane, therefore x plus sign changes here, minus sign changes here, that is inverted, therefore minus 1. Sigma v xz, sigma v x, z is perpendicular axis, therefore sigma v xz means this is the plane, there is no change. Okay, no, therefore it is 1. Sigma v dash yz is a perpendicular plane, therefore plus and minus interchange, therefore it is minus 1. Okay, so 1 minus 1, 1 minus 1, which is that IR 1 minus 1, 1 minus 1, that is B1, that is it transforms as B1. This is B1. Actually, this is B1 is Px is also the Px orbital transforms as B1 or X coordinate transforms as B1. X and Px is the same, will be same. Okay, irreducible representation for X coordinate and Px orbital will be same. Okay, it is B1. And Py orbital. Similarly, in the case of Py orbital plus minus sign here, it is y axis. E no change, C2z, then it is an axis perpendicular to this orbital, therefore plus and minus interchange, therefore minus 1, sigma v xz interchange minus 1, sigma v yz, which is Py orbital, therefore plane is like the plane of the paper, therefore no change, therefore 1, 1 minus 1 minus 1 1, and that is this one. 1 minus 1 minus 1 1, that is y and Py also transforms as B2. Okay, that is it is B2. Py orbital transforms as B2. And Pz case, this is z axis. E transforms Pz as itself, no change. C2 no change. Sigma v xz no change. Sigma v yz no change. Therefore, it is A1 operator. That is z coordinate and the Pz orbit will be same. Transformation of z coordinate and Pz orbital will be same. Transformation of y coordinate and Py orbital will be same. Transformation of x coordinate and Px orbital will be same. Therefore, we say that. Therefore, we are saying that x transforms as B1 or Px transforms as B1, y transforms as B2 or Py transforms as B2, z transforms as A1 or Pz transforms as A1. Okay, and s orbital, that s orbital is being spherically symmetrical and transforms according to totally symmetric representation. S orbital is we know that a spherically symmetrical orbital. Therefore, it transforms according to totally symmetric representation. In this case, it is A1. So, S orbital is not indicated in any character table because in every character table, the first irreducible representation is a totally symmetric representation. I told you. Okay, in every character table, first IR is a totally symmetric representation, and that is the transformation of S orbital actually. That is actually not shown in the character table, that is, but you have to keep in mind that is S orbital transforms as the totally symmetric representation. And there is also another thing, this XYZ coordinate. Actually, these XYZ are XYZ vectors. Okay, this coordinate is actually XYZ vectors. So this thing, that is XYZ represents a vector. There is any vector in the x direction, transforms as B1. Okay, thus translational motion in x direction, and the component of the dipole moment, that is mu x, also transforms as B1, and mu y, component of the dipole moment operator, mu y, also transforms as B2. So okay, from this knowledge we are predicting the vibrational spectra of the molecule. We will discuss it later. The application of character table predicting the vibrational transition is actually from this point of view, that is the dipole moment vectors transforms as actually XYZ coordinate. Okay, dipole moment vector mu x transforms as x coordinate, that is B1, mu y transforms as B2. I think we can discuss it later. Sometimes you may not understand this thing. Okay, we will discuss it later in the application of character table. Okay, and now another thing, in the area 2 there is another some terms, that is Rx, Ry, Rz. and that indicate transformation of rotational motion of the molecule about x, y, z axis. These Rx, Ry, Rz indicate the transformation of rotational motion of the molecule about x, y, z axis. In the C2v point group, Rx transforms as B2, Ry transforms as B1, Rz transforms as A2. You can look at here. Rx transforms as B2, Ry transforms as B1, Rz transforms as A2. Okay, that we can discuss. Let us find out the character of rotation Rz. We are considering Rz. The rotation may be represented by a curved arrow about the z-axis. These are the x, y, z axis. This is the rotation. We are indicating rotation like a curved arrow. Okay. Then E, the operator E. On operating the operator E, the arrow is unaffected. Therefore, character is 1. On operating C2, C2 operating on this vector or on this arrow, then it is also, this is z-axis, therefore no change in the arrow. Therefore, its character is also 1. And sigma v xz. Sigma v xz. On sigma v xz is, we are cutting through this plane. Sigma v xz plane. Therefore, the arrow become inverted. The left side of the arrow move towards the right side and the right side to the left side. That is, they are inverted. Therefore, character is -1. By cutting like this, the arrows are just inverted. Therefore, character is -1. And sigma v dash yz, same as that of sigma v xz. That is cutting like this, a plane like this. Okay, then the arrow is inverted, therefore character is -1. That means the characters are 1 for Rz. We are considering Rz. 1, 1, -1, -1. Okay, it is related to IR A2. Consider here. Yes, 1, 1, -1, -1. That is R. Therefore, basis for this A2 operator is Rz. Rotation, Rz means rotation about the z-axis. Similarly, rotation about the x, y axis, that is Rx, Ry, transforms as B2 and B1 respectively, we can understood like this. Considering a vector on or an arrow on the x axis and y axis, we can actually find out the transformation properties of Rx and Ry, and we can see that it is equal to Rx transforms as B2 and Ry transforms as B1. You can check by yourself. Another important thing, that is microwave spectra of molecules will be due to this intrinsic rotation of the molecule. This Rx, Ry, Rz represents actually the intrinsic rotation of the molecule, and microwave spectra of the molecule is due to this intrinsic rotation, and its application we will discuss later. Okay, but by looking at this Rx, Ry, Rz things, we can predict the microwave spectra, and we will discuss about this later. And another thing is area 4. In area 4 contains binary products x, y, z, including squares and the linear combination. Area 4 contains binary products of x, y, z. I already told you later. Told you earlier. That is x, y, z, binary products of x, y, z. That is x, y, x, z, y, z, etc. And their squares and linear combinations are present in area 4. We can check what are the transformation properties of these combinations, that is binary products and their squares. Okay, first we know the transformation of x, y, z coordinate we already discussed. In the x coordinate E, no change, therefore character is 1. C2, x coordinate changes to -x, therefore it is -1. Sigma v xz operation, x coordinate changes by itself, no change, therefore 1. Sigma v dash yz, x coordinate changes to -x, therefore it is -1. And y, the coordinate y, E, no change, C2, y become -y, therefore it is -1. And sigma v xz, y become -1, therefore it is, -y, therefore it is -1. Sigma dash v dash yz, y become y itself, therefore it is 1. and Z transformed by itself by all the operation, therefore all the characters are 1. This we have already discussed, xy, transformation properties of x, y, z. And their products can be easily obtained by multiplying the characters of the corresponding coordinates. That is for xy, x into y. That is for xy, what is the transformation property of xy in E operator? We simply multiply x and y transformation 1 into 1, that is it is 1. Okay, and here xy minus 1 into minus 1, that is 1. 1 into minus 1, minus 1, minus 1 into 1, that is 1. Therefore 1, sorry, minus 1 into 1, minus 1. Therefore 1, 1, minus 1, minus 1. And what is that that thing? 1, sorry, here 1, what was that? Okay, 1 minus 1, 1 minus 1. Where is that? 1 minus 1, 1 minus 1. Yes, 1 minus 1, 1 minus 1. That is, sorry, we have to look back. Yes, xy, 1 minus 1 into minus 1, 1, 1 into minus 1, minus 1, minus 1 into 1, it is minus 1. Therefore, it is 1, 1, minus 1, minus 1. C2, okay, sigma v xz, it is 1, yz, it is minus 1, yz. Okay. Okay, therefore xy transforms as xy transforms as 1, 1, minus 1. Yes, correct. The xy transforms as a2. Here xy is here. It is a2, 1, 1, minus 1, minus 1. Correct. Okay. Therefore, it is a2. This character is, this is the irreducible representation is a2. Sorry, this one, a2. 1, 1, minus 1, minus 1. Therefore, xy transforms as a2. Next, xz. We are considering xz. Okay, xz. X into z. That is 1 into 1. 1. Minus 1 into 1. Minus 1. 1 into 1. 1. Minus 1 into 1. That is minus 1. 1 minus 1. 1 minus 1. Xz. Okay, you can look. We can look here. 1 minus 1, 1 minus 1. Therefore, yes, the xz. Xz is here. 1 minus 1, 1 minus 1. Okay, it transforms as b1. So IR is b1. Okay, it is b1. B1. Okay, next we are considering xz. Sorry, yz. Yz, y into z. 1 into 1. 1. Minus 1 into 1, minus 1, minus 1 into 1, minus 1, 1 into 1, 1. Therefore, 1 minus 1, minus 1, 1. Which was that? 1 minus 1, minus 1, 1. Yes, yz. It is here, yz is here. Okay, it transforms as b2. It transforms as b2. Okay, we get, and we are taking the squares. Okay, all the characters are 1 and minus 1. Therefore, their square is equal to 1 itself. Therefore, all these are 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Am I correct? Okay, because we are taking the square. X, here 1 square, minus 1 square, 1, 1 square, 1, minus 1 square, 1. Here also y square. All the characters are 1 and minus 1. Therefore, we are taking the square. We get only 1. Therefore, all the characters are 1. Therefore, all these are a1 operator, sorry, a1 IR. Okay, therefore, the x square, y square, and z square are transforms as a1. Yes, okay, look here. You can see here in the character table, x square, y square, z square transforms as a1. Okay, clear. And these are also the transformation of properties of d orbital. All these things, that is, all these binary products, and the squares are the transformation properties of d orbital also. Consider dz orbital. Okay, this is dz orbital. Not dz, dyz orbital. This is the y-axis, this is z-axis. Orbitals, the lobes are in between the axis. Here plus sign, minus, minus. This is the shape of dyz orbital. Then operation E, no change. 1. C2z. This is z-axis. So on C2z operation, that is rotating through this axis. Therefore, this plus 1 become here, minus become here, minus here, this plus here. Plus and minus interchange. Therefore, it is minus 1. Sigma v xz. Okay, xz is perpendicular to this one. Xz plane is this one. This is y, this is z. Therefore, x is perpendicular. Therefore, this plus and minus interchange. Therefore, minus 1. Sigma v yz. Yz is this plane. No change. Therefore, 1. Therefore, 1 minus 1 minus 1 1. Which was that? 1 minus 1 minus 1 1. That is B2. Yes. 1 minus 1 minus 1 1. That is B2. That is yz. Yz is here. Property or a transformation property of yz and dyz will be equal. Okay, no doubt that. Okay, therefore it is B2. Therefore, dyz orbital transforms as B2 and dxz. Same shape, but it is x-axis, it is z-axis. Therefore, E no change, C2z. Here also C2z, the plus and minus interchange, therefore minus 1. Sigma v xz. Sigma v xz is plane, no change, therefore 1. Sigma v yz is plane, this plane, therefore plus and minus interchange, therefore it is minus 1. 1 minus 1, 1 minus 1. What was that? 1 minus 1, 1 minus 1. 1 minus 1, 1 minus 1. The xz, that is B1. It is B1. Okay. B1. Therefore, dxz orbital transforms as B1 and dxy. Here also, this is x-axis, this is y-axis. Lobes are in between the axis. E no change. C2z. C2z is perpendicular this plane. Therefore, x and y, I think C2 on C2z operation, this plus become here. This minus become here. No change. Therefore, it's 1. 180 degree, C2 means 180 degree rotation. On rotation 180 degree, this plus come here and this minus come here. No change. Therefore, 1. And C sigma v xz. Sigma v xz is a plane perpendicular to the this plane. Therefore, this plus and minus interchange, therefore minus 1. Similarly, sigma v yz plus and minus interchange, therefore minus 1. Therefore, 1 1 minus 1 minus 1. 1 1 minus 1 minus 1. That is xy here. Xy here. dxy and xy transforms similarly. Xy and dxy orbital transform similarly. Therefore, A2. And that is A2. A2. That is dxy orbital transforms as A2. That is the combination and the squares, actually the transformation properties of d orbitals. We can check out the other d orbital also. You can do it by yourself. And the last thing we want to know that about the area 4 is that another important significance of this area, that is area 4, is that it gives the transformation properties of polarizability tensor of the molecule. Okay. That is, the area 4 also gives information about the polarizability tensor of the molecule. Molecules undergo polarization when they are subjected to external magnetic field. This is called induced polarization. When a molecule is subjected to external magnetic field, it undergoes polarization. That is called induced polarization. And this property of the molecule is related to Raman spectrum, Raman activity. Okay, you might have studied that Raman spectrum arises due to the change in polarizability. Okay, and the Raman activity depends on the polarizability of the molecule. And it may be, we will discuss with this thing later more detail. It may be stated that binary products x square, y square, z square, and xz, yz, and xy appearing in area 4 indicate the transformation property of polarizability tensor. Actually, the area 4, that is the area 4 containing x square, y square, z square, xz, yz, and xy indicate the transformation property of polarizability tensor, and from these properties we can predict the Raman activity of the molecule. So area 4 is very important for Raman activity. Area 3 is very important for IR activity. This will discuss later about the application of group theory. Okay, anyway, this is the character table for C2v point group. Okay, I think you have you maybe understand this thing, and please read the textbook very well. Today itself, after watching the video, please read the textbook very well and understand more detail. Okay, thank you.